Hi and welcome to MPhil Physics Tutor. Recently I've been doing a lot of sessions on basic electromagnetic induction with my year 13s, so that's just a few months before their A-level, so I figured let's do a video on it so they can watch and you can too. So let's get on with it. So we're going to start off by considering how the movement of a charge can be considered to be a current. Well, it's not really that tricky because you know that current equals I is change of charge over change of time, or in other words, as we like to say it, flow of charge. Now a proton is obviously a positive charge, so if we move it to the right we have a flowing charge, therefore it is a current, and in this case it's going to be a current to the right, and the reason it's right is because current is defined as being the direction the positive charge would flow. So a proton going right is a current to the right. An electron, on the other hand, moving to the right is considered as a current going to the left because, as we just said, current is always the direction of a positive charge, and this is in the opposite direction, so currents to the left. Now what's this got to do with anything? Well, if you imagine a piece of metal like a bit of wire or an iron bar or something, if you move that through a magnetic field, you're going to put a force onto the electrons, and the reason for that is really pretty straightforward. So let's just unpack it a little bit. So if this is a metal, I don't know, it could be a copper, it doesn't really matter, it's just some metal. All metals, as you know, have delocalized electrons, so we'll put a few of them in, just a few. Along with that, there are positive ions in the centers. Now these positive ions are fixed in place and can't move. So if we bring the rod to the right, give it a velocity, a constant velocity moving right, through a magnetic field which is coming down, so we have magnetic field this way, velocity that way, we can then consider the individual electrons. But remember, they're moving in this direction, so they represent a current going to the left. So if you now bring out your Fleming's left-hand rule, first is field, which is down, second is current, which we just said is to the left. That means there's a force to the front. In other words, each electron, or each delocalized electron at least, is going to feel a force in this direction, and because it's delocalized it can move. The net result of that is that a whole bunch of these delocalized electrons will accumulate down at this end. Now the positive charges, they also feel a force, but because they're fixed into the lattice they can't move. The other end of the rod loses electrons that get sucked or are pushed, as it were, to the front, so the back of the rod becomes positive. Now what we've done now is create a distribution of charge that isn't the same everywhere. If we were to put a voltmeter, say, across here, we would measure a voltage. In other words, we've created a source of electricity, or an EMF, by moving a conductor through a magnetic field, and this is the basis of the process of electromagnetic induction. Induction is a word that means to create, so we could say something like it's from the word induce. So you induce a sense of fear in someone if you say set them an extra homework one day for some reason. You're inducing something in them, fear in this case. So electromagnetic induction, we're inducing an EMF which we can measure on this voltmeter. By the same sort of kind of token, if we were to then connect a wire to each end of this rod, like so, we could in theory measure a current. You'd probably want to put some kind of resistor in there to limit the current, but that's kind of irrelevant really. The fact is that we will measure a current flowing like this. In other words, the EMF is kind of, to some extent, more basic than the current, because you can't have a current without an EMF. Although that's an interesting discussion in itself. Can you have current without an EMF? Right, so this is the basis, as I said, of electromagnetic induction. So you really need to get your heads around this. You might think, well, so what? But actually this is a really common event. So for example, the Earth has a magnetic field, and at some places on the Earth the magnetic field has quite a significant downwards component. This means that if a plane flies in the right direction through those magnetic field lines, those field lines get cut and an EMF can be induced across the wingtips of the plane. I've made a video on that which you might like to check out. It's a disappointingly small EMF though. I was hoping it might be like 1,000,000 volts or something, but it isn't. It's much smaller. Okay, so if you're going to get to grips with electromagnetic induction, you need to be clear in your mind about a couple of magnetic fields. So let's just revise these, just so that we can say we've done them. So this, I'm sure you recognise instantly, is your bog standard bar magnet. So in a bar magnet, the field is symmetrical about this kind of midline, as you can see, and the field lines are curved. They come out of the North Pole and obviously into the south at the other end. And most bar magnets are made of something called iron, though there are other metals like cobalt that you can make into magnets as well. And as you know, some of these lines will curl around to form these loops. Okay, so nothing new there. You should be totally happy with the field around a bar magnet. So why am I bringing that up? Well, I'm bringing it up because we can also create something very similar like this. So when you get a lump of, say, iron again, and we wrap a whole number of neat turns. Look how neatly I've created this little picture here to show how neatly these turns are made. And then we're going to shove a DC current through in this direction. Now you might remember diagrams that kind of look a bit like this. So this represents a wire that's coming out of the page or into the page, and if we put a dot in it, that kind of means that there's a current coming out towards us. Now the field around a wire that's carrying a current is circular, so I just put a couple of field lines in, and you can work out which direction that field is going in using the right hand screw rule. So the thumb points out, the fingers show that in this case the field is anti-clockwise, like this. Why am I reminding you of this? Because, you know, it's the basis of what's going on here in this solenoid or this coil. So if we have a wire going in the other direction, so this second wire is carrying current into the page. Again, use the corkscrew rule. This time the field lines are travelling and clockwise. So this one is anti-clockwise, this one is clockwise, and you'll notice that in the middle the field lines are travelling in the same direction. And because magnetic field lines are a vector, or lines of flux are vectors, they add. Now this is just two single wires. You can think of each of the turns in my solenoid here as being like one of these single wires. And we've got hundreds of them, or potentially hundreds. And they're not just points pointing in one direction, they're coming around in circles around the iron bar. So each little section of the wire, each minute bit of it, contributes to these circular field lines. Anyway, the whole lot add up to create, hey presto, the same shape of magnetic field as a bar magnet. Now this is wonderfully useful because now we have a bar magnet that we can control. When you get a bar magnet from barmagnetsrus.com, it's a fixed strength and it just carries on being a magnet unless you heat it up too much or stick it through a magnetic field or something. With a solenoid though, you can change the size of the current, you can change the number of turns, you can change how much iron you've got, etc. And this means that you can change the strength of the magnetic field around it. And this is just massively useful. So here's a neater diagram I did. So if we were to increase the current, perhaps by putting in a second cell, that wouldn't increase the current though, would it? But yeah, it would, because it would increase the voltage, which would therefore increase the current. That will mean that it will get more field lines. They'll be closer together. I'm sure you remember this. If we swap the batteries around, that means that the current will flow in the opposite direction and the arrows on the field line will swap over. So let's consider now, this is like the meat and two veg now of this topic. We're going to consider what happens if you have a solenoid and you put an AC current into it. So this is an alternating current. Doesn't matter what voltage it is or what the frequency is really. But what we know is that the current is going first in one direction and then it flips over and goes the other way. Now we probably should think about what this looks like on a graph. So alternating current is basically a sine or a cosine wave, depending on how you want to think of it. It has a shape like this, nice and regular, nice and symmetrical. So here's time, up the side here is current. So this will be current in one direction because it's positive, and then negative in the other. So let's just point a couple of things out. Firstly, there are points, as you know, where there are no current. if there's no current flowing in the solenoid, you're going to have no field lines. There are points when the current is really quite strong going in one direction, and then points when it's quite strong going in the other direction. Now in those 2 points, what you find is that the field lines will swap direction. So one sense, or one part of that curve, say along the top part there, so this is our current curve, we might have a south pole at this end. And then what happens is we flip the current around the other way. So this is where we have a south, we flip the current into the other direction, and now we have a north at this end. And obviously the other 2 ends will be north in this case and south in that. So what's happening as the current goes from nothing, there are no field lines, then gradually there are more field lines building up as it heads towards the top. Then we reach a peak density of field lines, if you like. Then after that point, we can see that the amount of current still travelling in the same direction is decreasing down to a point where there are no field lines. So we have no field lines here, an increasing number of field lines pointing south, well, pointing with the south pole at one end, then a decreasing number of field lines down to 0, and here the field lines start building up but going in the other direction, reach a maximum, decrease away but still in the same direction, and then they change direction again as we go back into the positive side. So in other words, the key idea here is that because we have a constantly changing current, we have a constantly, really important phrase this, constantly changing amount of flux, or constantly changing set of flux lines. Let's leave it like that for the moment. A constantly changing set of magnetic flux lines. So let's just get rid of this for a minute. I wanted to say a constantly changing set of flux lines. Not only are they getting stronger and weaker, but every half cycle they're changing direction. Now, that's going to be really important, this idea. Okay, last bit for now then. I wanted to go on and talk about coils. Now coils are kind of a difficult concept for students to get their heads around. So what on earth am I drawing here? Well, the way to think about a coil, especially for AQA, they do this a lot, but the other syllabuses do this too, is this blue bit in the middle is what they know as a former. It's what you wrap the coils on. So the way I like to talk about it is to think of a lollipop stick. So you know when you get your Fab Ice lolly or your whatever ice lollies you kids eat these days, you can imagine that you get one ice lolly. I'm not going to bother drawing curves. But there's a nice lolly stick, and then you get another lolly stick like this, and then you get a third lolly stick like that, and you stick them together. Don't ask me how, but you just do. And then your last lolly stick like this. Now what you now have is like a wooden frame in the shape of a square hole. So you could literally, if you wanted to, stick your fingers, you know, through the middle here. Oh, I can't draw, but you get the idea. You can stick things through the middle of this core. So the core is hollow. Now, then what you would do, pretty simply, is to just wrap lots of turns of wire. So you wrap a turn of wire around here, then around here, then it goes around the back. Obviously you can't see it. Goes underneath, can't see it there. Comes up again on this side. So we have a whole bunch of turns like this. And you can see I'm only going to draw a couple and round again. Then obviously 2 wires come off here somehow and they're connected to a voltmeter or something. So that's the basic idea. You have a former, you wrap turns around it. Now if you go again to the mysterious magnetsrus.com and you buy one of these formers, they might be, you know, this long. I've only drawn it the width of a lollipop stick, but it might be this long with thousands of turns of wire on. I've only got 2. What we are interested to think about here is how many lines of flux. So what we have here, what I've represented is these lines of flux in red and a couple yellow at the bottom. So what are these flux lines? Well, they're, to some extent, they're imaginary lines that help us describe what happens with magnets, how they work. What it's not doing, there isn't something flowing from one end to the other, or at least nothing that we can see or touch, but it behaves as if there is. So there are a set of imaginary lines. Now I've drawn them, you know, with this much distance between, but it's totally arbitrary. I could have drawn more or less. The point to take out here though is that all the red ones, of which I think there are 7 or might be 6, they're all going through the coil. So these lines here are what we call linked. I'll talk more about this perhaps in the next session. Whereas these yellow ones down the bottom here are outside the coil. So, you know, we're not really interested in them because they're not going through the middle. So far so good. Now the last thing about this then for today's session is that very often these coils have a center axis, which is often just drawn as a dot and then a straight line coming down like this and then coming out the other side. So that's probably a solid line at the top. And this is a center of rotation or an axis. So the whole coil might rotate in that direction around this axis. So what that means is that this point here is coming round in a circle horizontally. So it's like this bit is moving out of the page towards us, gets to the middle, which will be kind of like here, and then carries on moving around. So it's rotating horizontally, and we'll have a lot more to say about that. So what I'm going to cover next is how the rate of change of flux leads to an EMF, a voltage developed in these coils, and we'll look in some detail how that works. So don't forget to look out for the next session. See you later.